Hello, so whoever is watching this, and today I would like to talk about Euler angles. So let's see. I studied it a bit today, and it's really weird way to show rotations. I mean, some people claim it's the easiest one so far, but uh, for me, what's easier? I mean, just have a rotation matrix, which just make a rotation matrix. We can rotate in any direction we want, and we have a good matrix for that. But I think I don't know. This one feels more fundamental for people. So the idea is simple. Not simple. I won't say simple. Suppose you have a x-axis, y-axis, and z-axis, and you have to do three rotations in three different ways. Like basically, you will have a rotation about the z-axis, then you will have a rotation about the y-axis, and finally a rotation about the x-axis. And depending on the convention, people might start with x, y, z, or z, y, x, whatever. Yeah. Mostly it is in this way: x first, z, then y, then x, or if not that, z first, then x, then y. We will stick to x, y, z, y, x. So how it works, I will show you. Suppose you have this 3D coordinate system and you just rotated this about the z axis. So what happens is slightly, so this z axis will be the same as it is, but this y axis will slightly shift. Let me change. Uh, so what I will do is I will make some color. So for z I will use red when I do rotation about z. For purple maybe for y, and dark blue for x. So when I do about z axis, what happens is I get new axis, right? I get something like this. So some angle psi was made up around this, and then once I did this, what I will do is now I have to do about y. So I will take this y axis, my new y prime and x prime. I mean new x primes. There is no x prime here. Now what I would do is I will just rotate it about the y axis. So now rotation will take place here, and what will happen is this x will get lifted a little. Okay, if I do it, if I see in the y prime point of view, anti-clockwise is considered positive, so anti-clock will be something like this. If you see, if your eyes are here, like if your eyes see towards the z axis, you will see anti-clockwise thing like this, and x will go down, kind of. Okay, let's not make it complicated, up or down. It will make some angle, right? You have to make some angle, and I will just keep it uh, however I want. Let's say something like this. So this x-axis will get lifted, and also this z-axis will get tilted, something like this. So now I got an extra angle. Let's call it theta. Now and finally, now this will be my z prime, and this will be my new x double prime, I would say. And now finally, what would happen is I will rotate about the x-axis, right? Finally, and when I rotate about the x-axis, now x-axis will be the same as it is, but now uh, what happens is how what would happen, this z and y would make some other angle. So basically z will become now z prime will be z double prime, and y prime, and so something like this. It's very weird. I'm not able to show this on a 2D plane, but that's how it is. I don't know if I can show this using Desmos, but let me try. I don't think I can do it, but so first of all, you will have a rotation about the z-axis, and then you will have a rotation about the y-axis. Y-axis green stays fixed, and then finally about the x-axis. And you can have some nice matrices for that. For example, you might have seen or not seen, I don't know. If you want to do, if you have an xy plane, if you have an xy plane and you want to rotate this plane with some angle theta, this can be done by just shifting x to uh, let me do it as a whole. Shifting xy, uh, how should I show it exactly? X will go to some x prime, y will go to some y prime, and the rotation matrix for that looks something like this: cos of theta minus sin theta, and here it will be xy. And let me check if that's correct. So assume that initially, so cos of theta, if I do the matrix multiplication, it will be cos of t times x plus sin of t times y, comma cos of t times x minus, am I doing it right? Okay, okay, I think it is sin of tx here. Sin of tx sin of tx, the I think minus here, and here it will be cos of t 1, cos of t 1, cos of t times y. Here it's a plus, and I think I should have been better in the notations. I mean, let me use y, capital Y, some initial point, capital Y, capital Y, no, it's capital X here, capital Y, capital Y, and then again I go back, capital X, and I just write, and I want uh, I need a tx, let me write a tx. Yeah, so I have all the points I need. So just think about it. Initially, where did it go? Initially, if I keep my xy as 1, so, and time 0, let me start from 0, 0 to 2 pi, step 0 0.001. Initially, if we keep it like this, and now let the time run, this is what happens. Okay, why is it going anti-clockwise? I wanted to go clockwise. What the hell? Let me keep it as I always mess up in the math, but let me just keep this as 1. I wanted to go in anti-clockwise, it's going in clockwise. I think 1 and 0. And if I start it, what? Come on, no, 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 no. Go like 1, 1. Yeah, and I will rotate it. No, no, no. Okay, okay, I have to come math, remat. There is supposed to be a plus here, and there is supposed to be a minus here. I think I also have a PDF. Let me check here. I don't trust these PDFs, but that's all I have. They give a minus, but no, no. I think I don't trust this honestly. No, 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 no. There shouldn't be a minus here. Minus plus. It all depends on what I want to see. So if that's the case, and this is how it should be. Basically, my initial vector here after some theta rotation will get shifted like this. Similarly, this one will get shifted like this. So yeah, here this should be positive overall. This whole side should be positive, but because of a little shifting in the x, I need a minus sign here. So let me just fix that up. This whole side is positive. Yeah, now here should be minus because of matrix multiplication. Now I am good. I am ready to do whatever I am about to do. So yeah, let's go. Let's do it. Yeah. So I just let the time start and it rotates. That's all its job is. Uh, so yeah, it was just a matrix multiplication. Cos of cos theta times x minus sin theta times y, sine theta times x plus cos theta times y, and that's it. And now uh, so now the question will be, how would I make it happen like this, and what does it really physically mean? Like, why would I need to do all these complicated orientations? Uh, so that is also a valid question. Look, if I want to just make it rotate about the x-axis, I have a very nice matrix for that. This is all I have to do. I will just keep it rotate about the z-axis. Actually, I will just do this. So it will be cos theta, cos of psi. Let's say psi about the z-axis, because that is the convention. Sine of psi, cos of psi. Oh, I mean minus sine of psi. This does it. Okay. This is rotation for about the xy axis. This is rotation uh, about the z axis on the xy plane, and the angle is phi. Similarly, I can do the same thing for a rotation about the y axis. So y axis will remain fixed here, and I can write something like this. Let me write down cos of, here let me use theta, cos theta, this will not change. And here because of the way the Cartesian coordinate is set, I will write a plus sine theta here and a minus sine theta. Don't worry about the pluses and minuses here, it's just a matter of clockwise and anti-clockwise. We can always fix it depending on what our conditions are. And then we have this will be about the xz plane, rotation about the y axis, angle is theta. And finally we have about the x axis. So this will remain constant, this will remain same, the x axis. And so we have cosine of phi. Okay, here a little writing mistake, theta, cosine of phi, and here we have minus sine of phi, and we have a sine of phi. And this is a rotation about the x-axis in the yz plane, and everything is nice, right? So what would I do? Like, suppose I have space, I have some point in space, I will just make it rotate. I will make it rotate about the z-axis in the xy plane with some angle, theta. I mean sorry, it's psi. And now what I want to do is, now in this new frame, like after all that, in that new frame I want to once the transformation has happened, in the new frame I want to do rotation like this. Sorry, in about the y axis, right? About the y axis. So to do that, think about it. I have to think what will the rotation matrix look in this guy's frame, that rotation, what is happening in my frame. What exactly I mean is, in my frame, of course, yes, if I hadn't done this RZ transformation, the rotation about the y axis would indeed be this. But now I have to look in this guy's frame, how, what is the rotation about the y axis in this guy's frame. The y axis in this new frame which I did the transformation is different now. I have to think in that point of view. And and I am pretty sure, I believe it will be done by something called similarity transformation. Basically, if you have a matrix in one frame of reference, you can just convert it into another frame of reference by some similarity transformation, which takes care of the same thing happening but in that coordinate system. Yeah, so I have to do that now, and I don't remember exactly what is supposed to be done in that. So let's keep that in mind. Let's see what I was thinking something like this. What if uh, so this is what has z happened, right? So this is x, y, z, psi. What if I just for a moment convert this back to my old space by taking inverse of this about xy, do that rotation in about my y-axis, do the rotation in what is that axis again, xz, xz, and then come back to my old, right? I can do that. So I can do that. So I think, yeah, this is the idea. First of all, I have some point in space. I will rotate this about this new axis. I mean about my old unchanged coordinate system z, in the z axis. But now I have to be careful. Now the new x prime I have got, I have to rotate it again, right, about theta. So what I can do is I have to do about the y dash axis, because this will be different. But this will be taken care, because this is nothing but uh, whatever r y x z is, with a similarity transformation, something like this, r z r z x y inverse. And so then finally I have got this x double prime and one last rotation. Now I have to do this with about the new x prime axis, and x double prime axis, maybe x prime, I mean y prime, and z prime, and both of this will change again. uh, yeah, so both of this will change here. How should I say, here z didn't change it, it will be changed after the rotation. Z didn't change here, right? So that's this z came here. Similarly this y came here. This is confusing, but I might it be confusing more. But so again this will be again done in similarity transformation. What I have to do is I have to think in y prime z prime of x, old x, but this time it will be uh, oh, it's getting too complicated. What would this, first of all, what would this matrix correspond to? Let me just write this down. This is equivalent of saying I did this r z of x y, r y of x z. Now I have to turn my come back to my old space. So what I have to do is, it will be something like this, inverse. And so it will be like r z x y, r y x z, and then inverse r z x y, r y x z. So finally I will get my new rotation. So basically if I want to do first psi, then theta, then phi, the matrix would look something like this actually. R of phi, z, what is this, x y, r of about my y axis, uh, about my y axis. Oh, xy is looking like xx, and here it's good, and it is x z, I guess, and finally about the x axis. Oh yeah, also the angle is theta here, and finally r of z, x y, and yeah, it is about 5. So all this combined, theta, I mean any vector I have. I want to check this now. I really want to check this. How would I check exactly? That is a good question. How would I check this? If this works. And it's weird, right? Remember the order was, first we have to do this geometrically, first we did this, then this, then this. But the matrix, what it is doing on this vector, is first it will do this, then it will do this, then it will do this. I don't know, that's weird, but I just considered everything I could, then I constructed, so I don't think this can be wrong. I can always be wrong, that there's a possibility, but and also I wrote this wrong. X here. Oh my god. Here it should be X and here it should be Z Y. Z Y. So here you go. And now I would like to read some Sakurai here. Let me just open some Sakurai. Uh, JJ Sakurai. I hope I have that book. It's a very nice book. Nice if you already have a little exposure. You just read quantum mechanics here and there, then it is nice. Otherwise, it's horrible, a nightmare. It's still a nightmare though. Okay, so they have something for rotations here. Euler angles. I would like to read that. Let's search it. Now I would read it like a school teacher, as a boomer. I would read it like a boomer, so just read with me. From classical mechanics, the reader may be familiar with the fact that an arbitrary rotation of a rigid body can be accompanied by three steps, known as Euler rotations. The Euler rotation language, specified with three Euler angles, provides yet another way to characterize the most general rotation in three dimensions. Wow, wow, wow! But I don't know how is that useful. This rotation is too complicated. Why do we use that? The three steps of Euler rotations are as follows. First, rotate the rigid body counterclockwise, as seen from the positive z axis from by angle alpha. Yep, alpha was psi in my case. Imagine now that there is a body y axis m, so to speak, in the rigid body, such that before the z axis rotation is carried out, the body y axis coincides with the usual y axis, referring to as space fixed y axis. Obviously, the rotation about z axis, the body y axis no longer coincides with the fixed. Yes, like this is complicated. So yeah, what we did, right? First we rotated about the z axis by some angle alpha. Look, before the rotation, the y axis was chilling where it was, but after we did the rotation about z axis, it got displaced. It got, it went somewhere else. So the new axis will be y dash because it changed. So we want to do this about the beta angle, whatever the new axis. About the new axis, we will rotate beta. This will, so basically, look, initially when you do z about z axis, x axis and y axis get displaced. Z axis remains same. And after that, when you do about the new y axis, z axis and x axis at that instant, those new x and z's we had, those get displaced. This stays as it is. Then we do with x the same thing. X axis, alpha, beta, gamma. So z axis also gets displaced because of rotation about the new y axis. And so now we have a z dash axis now. Final rotation. Oh my god. Okay, they are doing some other rotation. Like I said, right? X. They are doing x. So okay, there are multiple ways to show rotations. Here in there his notation, he doesn't like the x-axis apparently. I can't do help for that, but all the I think all the skills and all the skills required are still same. But okay, he will rotate the z-axis. What I was doing previously, I was rotating x-axis, I mean z-axis first, then I was rotating my new y-axis, and then I was rotating my new x-axis. But he's like, no, screw it, we won't do that. I will rotate my z-axis, I will rotate my y-axis. Come on. And I will rotate my y-axis, z-axis again, the new z-axis, of course. Yep, I don't know why, but he wants to do that, so who will stop him? So let's use this notation. I think even this covers all the possible rotations there are, so why not? Why not? So alpha, beta, gamma. So alpha, beta, gamma, and this is what he's saying: alpha, beta, gamma. He will do the rotation about z-axis, then a rotation about the y-axis, and then finally a rotation about again the new z-axis. Order matters. Yes, of course, order matters. I don't know what is playing around y-axis, x. I don't care, man. Just show me the physics. Okay, you win. First z, then y, then again z. I got it. I will do this. Okay, I will follow. It's okay. Okay, quantum mechanics. Like I was talking, and yeah, whatever I was talking before, you have to be careful. Like the rotation about the old YZ axis will be something like this, right? You have to be very careful about it. And so finally, and also this, how can we forget this? Damn. Okay, my maths is not that bad after all. I am so happy about it. Fuck yes, 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 yes. This is perfect. Perfect. My logic was right. Okay, good, 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 good. Perfect. You see, rotation will happen in this order, but we have to consider this order because why not? Because you every time you're doing a rotation, your space is getting changed, and you have to consider the change in the space itself as well if you want to get the coordinates right, which is what happening here. Yes, perfect, perfect, perfect. I like, seriously, so perfect. And so let me read this down. He has this Euler angles available here. The meaning of the right hand side is as follows. First, bring the body y-axis of figure 3 back to the original fixed space by rotating clockwise about the z-axis by angle alpha, then rotate about the y-axis by angle beta. Finally, return the body y-axis to the direction of y by rotating about z, blah blah blah, and by finally the equation tells us not affect this equation in single rotation about the y dash axis in beta. To prove this assertion, let us look some math. So we have this. Yep. So I would like to just do a firm revision again. This is so cool, at least for me, because I'm able to understand this stuff finally. It was very almost next to impossible for me. I was hitting my head like anything for last, I don't know, 6 or 5 months. So I have an XYZ axis. First, what I would do, I would rotate about the Z axis, right? I have some vector. I will do a rotation about the Z axis, and this becomes R prime, right? And then I do a rotation about the new prime, which I got because of that rotation about Z. and I get some other vector, and finally I have to rotate about again about the new z prime axis. Now I get this finally. So finally let me see. So basically you had a vector and you rotated this about the z axis, right, about the z axis on the xy plane. Now when you are trying to do this, now when you are trying to rotate this about the new y prime axis you got about the z and x prime frame, you have to be careful because this is the new space. So how would that look in the uh, how would that look in our space? That is also a problem. So first of all, what you do, this thing, how would it look in our space? uh, so in his space, right, in that space, what you do is first take the rotation which is supposed to be first this the thing which we have here, convert it back to our old space. So convert it back to our old space, then rotate whatever is supposed to be in your space, and then send it back to the space which is our rotated space. So basically this is a similarity transformation, right? So this would become something like this. uh, so something, this would become something like this now. So this will be rz xz rz r of x z z times ry of x. Okay, well, how is this xz? This is xy. Oops, sorry, xy. Yeah, xy. xy and rz of xy inverse, and not to forget we already had an r rz of xy, and now we have this. Now finally we have to do this now we have to do another rotation about the uh, z prime axis, the new z prime axis we have about the new z prime axis we have. And what would this do is, uh, let us just do it, right? We have to rotate this about the new z prime axis we have, and both x prime and y, both x and y have changed because of all those rotations. And on what do we have to do this? We have to do this on this rz of xy and rz of xy and what is that? And yeah, also not to forget, this was an alpha rotation. Then we wanted to do a beta rotation. So alpha, beta, alpha, and then again alpha, beta, alpha. Oh, xz of course, and alpha, and which gave us alpha, beta. Now again, since we have to do this, we have to come back to our old space. See how, so we have to come back again to our old space. See, rotate it and then convert to its space. So basically whatever this transformation is, take its inverse and put this here, and you are done. So what would you get is rz 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 alpha, beta, gamma, and yeah, it is a y here of course, and I don't need to write xy here or xz here, right? It is automatically understood. So this is equivalent of what were we doing before? taking the z about the z axis doing an alpha rotation. Then about the new y prime, about the new y prime, about the new y prime doing beta rotation, and about the new z prime doing a gamma rotation. Okay, these two are equivalent. Whatever will you get here, same thing will be, same orientation would you get here. That's very nice. Like, I don't know how much thankful I mean. I'm just able to understand all this, being able to do all this. So that's nice. So let's just put z prime, and now what more is Sakurai telling me? Okay, now we will do this Euler thingy in a spin. In a cartoon picture, just some atom, electron having spin orbital, whatever it is, it's just rotating about different axes. I don't know, it's chaotic, it's crazy. Uh, so I don't care how it's rotating. Quantum mechanics, just stay out of my way, please. And did I messed up my razor? No, I didn't. So basically, he has written d alpha beta gamma, d of alpha comma beta comma gamma. This is equivalent of, and yeah, these matrices are just fancy of way of rotating. Don't get scared by them. E power minus I sigma 1 uh, uh, of alpha by 2. I mean, let's see what has it written. Yes, 2. I don't know why is there a 2 factor here, but let's see. E power minus I by sigma 2 by 2, and finally e power minus I sigma 3 by 3. And now so all possible rotations are done, and I do some math, like I split things up, I do this, I do that, I don't know what not. Mm-hmm. Okay. Okay, I don't know, somehow the recording was stopped, so whatever I said, maybe a lot of it just vanished. So here is just a recap. I did this this this. So much of thoughts were given behind this, so much of logic was there. So if you skipped it, missed it, then you missed it. I can't do much, sorry about that. But basically, yeah, this is the most important result, like, if I can say, most important result. How we can write uh, rotations using the concept of similarity transformations, how it makes rotations more simple. I mean, at least that's the simplest tool we have. It is definitely not simple, but everything else is just harder than it, so that becomes the most simple one. uh, so then these are like Wintrins in insights which are very important. Okay, so these matrices are called d half of alpha beta gamma, and we just write them like this. And how did these came? They have their own what should I say, story some other day, but it's also logical, I guess. Like they spent a lot of time on that. So right now that's it for now. Thank you very much for watching whatever.